Welcome to my channel. Today we are going to solve two problems related with the topic limit cycle oscillation in a recursive system. So already we solved two problems from this limit cycle oscillation. So this problem is somewhat different from the previous two problem. Okay, so you see the question, study the zero input limit cycle oscillation of a digital system described by y of n equal to 0.9 y of n minus 1 plus x of n. Okay, so this is the system equation. So here y of n is the output and y of n minus 1 is the previous output, x of n is the input. Okay, so here with x of n is equal to 0. So the input applied to the system is 0, they given, as well as y of minus 1 is equal to 12. So the previous output, okay, that is the output of this given system at time n equal to minus 1. It is given as 12. So the previous output stored in the system is given as a 12. Okay, so the question is find the deadband. So we have to study the limit cycle oscillation behavior of this given system, as well as we have to find the deadband. Okay, so this question is a December 2015 and 2008 question. So in previously we solved two problems related with this topic, limit cycle oscillation. So in that the y of the previous data, y of minus 1 value is given as in fraction. Okay, but here the y of minus 1 value is given as a decimal 12. Okay, so that is a difference. So we are going to solve the problem. So first you just take down our given system equation. So our given system equation, y of n equal to 0.9 y of n minus 1 plus x of n. Okay, so first one we are substituting, that is we are going to calculate output of this system at n equal to 0. Okay, that is the time n equal to 0, we are going to calculate the output. So put n equal to 0 in our system equation. So y of 0 equal to 0.9, y of 0 minus 1. So y of minus 1 plus x of 0. Okay, so here you see the output at time n equal to 0 is depends on input applied to the system at n equal to 0, as well as the previous output y of minus 1. Okay, so here the y of minus 1 value and x of 0 value is given in our problem. So you see the input x of n is 0. Okay, for all time, for any value of n, the input applied to the system is 0. So that's why the x of 0 value is a 0. Okay, and y of minus 1. So in our problem, the y of minus 1 value is given as 12. So instead of this y of minus 1, we have to substitute 12. So y of 0 equal to 0.9 into 12 plus 0. Okay, then so if you are multiplying, you can get 10.8. Okay, so in this product, okay, so here the 0.9 multiplied with this y of minus 1, you know, for this product only we are going to perform the quantization operation. Okay, so in this here the number, that is the y of 0 value, we got it as 10.8. Okay, so here instead of that is we have to convert in order to perform the quantization process. So this decimal number we have to convert into binary, and in binary we are doing the quantization in previous problem. Okay, but here the answer is 10.8. Okay, so in this we are going to do the rounding process in a decimal digit directly. That is 10.8 means the 10.8 decimal number. If you are performing the rounding process, okay, so rounding process, it can be approximated to 11. Okay, since the 0.8, so this fraction is greater than 0.5. So that's why after rounding, so this decimal number 10.8 we can convert into 11. Okay, so here we used the rounding for quantization as a decimal directly. Okay, so this 10.8, after rounding we can get the answer 11. So y of 0 answer is 11. Then next one, we are going to calculate the output of the system at the next time n equal to 1. Okay, previously we calculated the output at n equal to 0. So next we are going to calculate the output at n equal to 1. So put n equal to 1 in our system equation. So this is our system equation. in this equation number 1, you just substitute instead of n 1. So y of 1 is equal to 0.9 into y of 1 minus 1 0. Okay, so y of 0 plus x of 1. And what about the value of x of 1 and y of 0? So x of 1 is 0. Okay, since in our problem, the input applied to the system is 0 for any value of n. So this x of 1 value is 0. And y of 0. So y of 0, just now, in previous step, we calculated. What is the y of 0 value? 11. Y of 0 means the output of the system at n equal to 0. At a time n equal to 0, we calculated as a 11. Okay. So you substitute, this is the quantized value. That is the exact value of y of 0 is a 10.8. Okay. So this is after rounding process, we can get the value 11. Okay, so that is the exact value of y of 0 is 10.8. So you just substitute that y of 0 value. So 0.9 into 10.8 plus 0. So the answer is 9.72. Okay, so for this product, we are going to perform the quantization. So here also, so for all steps, we are doing the quantization in a decimal directly. So the 9.72. So 9.72, it is after rounding process, you can get 9. So this answer is greater than 0.5. So that's why it is rounded to 10. So y of 1 value we calculated as a 10. Okay. Then the next one, the time n equal to 2, we are going to calculate the output. Okay. So up to which one we are going to calculate means, so the output becomes constant. Okay. Again and again, the same output, it will come after some time. That is call it as a limit cycle oscillation. So up to that one, we have to calculate the output. Okay, so you see at a time n equal to 0, the output is 11. At a time n equal to 1, the output is reduced to 10. Similarly, we have to calculate at a time n equal to 2. Okay, so if n equal to 2 means, so you substitute in our given system equation. So y of 2 equal to 0.9 into y of 1 plus x of 2. Okay, so here you just substitute x of 2 value and y of 1 value. So x of 2 value, already you know it is 0. Y of 1 value, just now in previous step we calculated. So that y of 1 value. Okay, so without rounding, what is the exact answer? 9.72. So you substitute here. So 0.9 into 9.72. So you can get the answer 8.748. Okay, so for this 8.748, we are performing the quantization in decimal itself. So 8.748, it is rounded to 9. Okay. So at a time n equal to 2, the output is reduced to 9. Okay. Similarly, we have to perform it for n equal to 3. So at a time n equal to 3, we are going to calculate the output. So y of 3 equal to 0.9, y of 2 plus x of 3. So x of 3 value is 0. Y of 2 value is 8.748. Okay. So you just, the answer is 7.8732. Okay, so after the 7.8732, if you are performing the rounding, so you can get the answer is y of 3 answer is 8. Okay, similarly, we have to perform it for n equal to 4. So at a time n equal to 4, so the y of 4 is 0.9 into y of 3 plus x of 4. So similarly, the y of 3 value, okay, so you just substitute. Then you can get the answer 7.08588. Okay, so the 7.08588, if you are performing rounding means it can be written as a 7. Since this fraction part is less than 0.5. Okay, so y of 4 value is 7. Okay, so again the output is reduced from 8 to 7. Okay, so that's why next we have to calculate the output at n equal to 5. So at n equal to 5, so we can get the answer is 6.377292. Okay. So after this one, if you are performing the rounding in decimal means 6.3, it is written as a 6. Okay. So again, the output is reduced from 7 to 6. Next, we have to calculate n equal to 6. Okay. So at a time n equal to 6, so the output you see y of 6 is equal to 0.9 y of 5 plus x of 6. So 0.9 into what is y of 5? Y of 5 value is this one, 6.377292 plus 0. Okay. So if you are multiplying, you can get the answer 5.73956. So 5.73956. If you are rounding, this y of 6 value as a 6. Okay, so you see the answer. Y of 5 is also 6. At a time n equal to 6 also, you can get the same output 6. Okay, then we can check one more time. So at a time n equal to 7, we are calculating the output. So at n equal to 7 also, 7, you see the y of 7 is equal to 0.9 y of 6 plus x of 7. So if you are calculating, the answer is 5.16561. Okay, so 5.16561. After rounding, what is the answer? 5. So again, the output is reduced to 5. Okay, so you see at n equal to 5, n equal to 6, same output we can get. Okay, but at n equal to 7, again output is reduced. Okay, so again we are going to calculate the output at n equal to 8. So if we are calculating at n equal to 8, we can get the answer is 4.64905. Okay, so the 4.6490, it is rounded to 5. So you see here, after that, this n equal to 7 and above 7, the output of this system, it produces some constant value 5. Okay, so that's why the system enters into limit cycle oscillations. Okay, so we can write so you see this, the system enters into limit cycle behavior whenever the time n is greater than or equal to 7. Okay, so you just see the outputs at n equal to 0. Okay, at n equal to 0, the output is 11. At n equal to 1, the output is reduced to 10. At n equal to 2, 9. At n equal to 3, 8. At n equal to 4, 7. At n equal to 5, it is reduced to 6. At n equal to 6 also, same 6 is maintained. At n equal to 7, 5. At n equal to 8, 5. Okay, after n equal to 9, 10 also, the same output is maintained. Okay, so that's why the system enters into limit cycle behavior. Okay, so we studied the behavior. So after that, we have to calculate the deadband. So what is the formula for the deadband? Deadband is equal to plus or minus 2 to the power minus b divided by 2 into 1 minus modulus a. Okay, where a is a coefficient. So this a is a coefficient given in our system equation. Okay, so here a is, so you see what is our system equation? Y of n equal to 0.9 y of n minus 1 plus x of n. This coefficient, this 0.9, it is called it as a a. Okay, so here we just substitute the value of a and b. So here b is nothing but number of bits used to perform the quantization. So here we are not at all using any quantization. Okay, so in decimal itself we are directly performing the quantization. So the number of bits used to perform the quantization is 0. So b value, you just substitute b value as a 0, and a, here the a is 0.9. So you substitute. So therefore the deadband is equal to plus or minus 2 to the power 0 divided by 2 into 1 minus 0.9. Okay, so the answer is plus or minus 5. So the deadband range is minus 5 to plus 5. This is our answer. Okay, so this is a very important problem, and similar to this problem, so one more problem you see, the next question, a digital system characterized by the difference equation y of n equal to 0.8 y of n minus 1 plus x of n, with x of n is 0 and initial condition y of minus 1 is 10. Okay, determine the deadband of the system. So similar to the previous problem, this is also the problem with the a value is different. So in previous problem, a value is 0.9, here 0.8. Similarly, the previous output, the y of minus 1 is given as 10. In previous problem, y of minus 1 is given as 12. Okay, so similar to previous one, here also we have to solve the problem. So you just take the given system equation. Okay, so we have to find the output first at n equal to 0. So you just substitute n equal to 0 in above equation. So y of 0 equal to 0.9, y of minus 1 plus x of 0. Okay, so here what is the x of 0? The input applied to the system at any time is 0. And what is the value of y of minus 1? So the y of minus 1 is given as, in our problem it is given as a 10. Okay, so you substitute. So 0.8 plus 10, so the answer is 8. So y of 0 is 8. Okay. Then at n equal to 1. Okay. At a time, the next time at n equal to 1, we are going to calculate the output. So y of 1 equal to 0.8 y of 0 plus x of 1. So anyway, the input is 0 and the y of 0 is just now previously calculated as a 8. So 0.8 into 8 plus 0. So the answer is 6.4. So 6.4, if you are performing the rounding process means 6.4 is approximated as a 6. So y of 1 is 6. Okay. Then we have to calculate the system output at the next time n equal to 2. So at n equal to 2, you see y of 2 equal to 0.8 into y of 1 plus x of 2. So here y of 1 value as a 6.4. Okay, so if you are calculating, you can get the answer is 5.12. So 5.12, it is approximately written as 5. So y of 2 value in decimal number is 5. Okay, so you see the output at the first time, output is 8. At the second time, output is 6. And the third time, output is 5. So next we have to calculate at n equal to 3. So at n equal to 3, we are calculating the output is 4.096. So 4.096 is approximated as 4. Okay. Similarly, we have to calculate it for n equal to 4. So if n equal to 4, you can get the answer is 3.2768. So 3.2768 is approximated as a 3. Then at n equal to 5, so at n equal to 5, the output y of 5 is calculated as 2.62. So the 2.62, it is approximated as a 3. Okay, so the 2.621, so output is approximated as 3. Then so here you see the output y of 4 is 3, y of 5 is 3. So next we will check for the next output at n equal to 6. So for n equal to 6, if you are calculating, the answer is 2.0972. So 2.0972 is approximated as 2. Okay. Again, output reduced. Then at n equal to 7, if you are calculating, the output is 1.6772. So 1.6772 is approximated as 2. So you see the output is reduced and output is maintained as a 2 for n equal to 6 and above 6. Okay, so that's why the system enters into limit cycle oscillation. So you see the outputs at a time n equal to 0, the output is 8. At n equal to 1, it is 6. N equal to 2, reduced to 5. N equal to 3, 4. N equal to 4, 3. N equal to 5, again 3. At n equal to 6, 1. N equal to 7, 2. Okay, 2, 2. So at a time n equal to 6 and above 6, the output of the system enters into limit cycle behavior. Okay, so therefore the dead band is calculated by, so what is the formula for the dead band? Dead band equal to plus or minus 2 to the power minus b by 2 into 1 minus modulus a. So here b is a number of bits used for quantization. So here the number of bits, that is, we are not at all doing the quantization in binary. Okay, so that's why the number of bits used to perform the quantization is, number of bits used is 0. So b equal to 0 and a, what is a? A is our coefficient. Okay, in our system equation, what is a? This is this 0.8. Okay, y of n equal to 0.8 into y of n minus 1. This 0.8 is a. So a value is 0.8. So you just substitute. So the dead band is equal to plus or minus 2 to the power 0 divided by 2 into 1 minus 0.8. So the answer is plus or minus 2.5. Okay, so the dynamic range is minus 2.5 to plus 2.5. The output it will vary. This is the dead band of the system. Okay, so thanks for watching my channel and please subscribe my channel for more videos. If you want to learn all lecture videos related with this subject, discrete time signal processing, digital signal processing, in our channel, in the name of discrete time signal processing, there is a playlist is there. In this playlist, all videos are available in order you can learn. Okay, and as well as in our channel, there is a complete lecture video and MCQ videos are available for the subject signals and system, electronic circuits to transmission lines and RF system. Then microwave engineering, antenna and microwave engineering is available. you just use it. Okay, so thank you. We will meet in the next video with one more problem.